All right, let's just jump right into this because you're gonna want to hear it. We're looking at some recent research that honestly pulls back the curtain on one of the strangest corners of quantum mechanics. It's a story about how particles that don't technically exist can somehow reach out and change the physical world. I know, it sounds like something straight out of science fiction, but as we're about to see, it is very, very real.
And there you have it. That's the whole paradox in a single sentence. Photons, particles of light that aren't even there, are changing how a real physical material behaves. And that's not a metaphor, folks. It's a direct observation from a brand new experiment, and it makes us ask a really fundamental question.
So this is the mystery we're going to unravel in this explainer. And to get to the answer, we've got to understand these super strange quantum ingredients that make this seemingly impossible interaction, well, possible. So let's break them down. To really wrap our heads around how non-existent particles can have a real-world impact, we first need to meet the key players, the particles themselves, and then the two very, very special materials they used in the experiment. Okay, so this first concept kind of redefines what a particle can even be. We're all used to thinking of real photons, right? The kind from a laser that you can actually detect. But quantum field theory says that even empty space is just humming with these fields. And virtual photons are these tiny, fleeting flickers in that field. You can't catch one, they're constantly just popping in and out of existence, carrying forces around. And here's the crucial part. A strong electromagnetic field can be absolutely filled with them even when there's no real light present at all.
And that brings us to our two materials. On the left, you've got boron nitride. Think of it like graphene. It's made of these hexagonal sheets. Now, this unique structure creates a very specific electromagnetic field inside it, a field that just happens to be the perfect home for virtual photons of a very particular wavelength. Then on the right, we have this unusual superconductor called KET. All you need to know about this one is that its ability to superconduct is tied to the vibration of one specific carbon-carbon bond. And here it is, the connection. The frequency of that bond's vibration perfectly, and I mean perfectly, matches the wavelength of those virtual photons living inside the boron nitride. It's an incredible setup.
So, we have a material that's basically filled with invisible ghost photons, and a superconductor that's perfectly tuned to their exact frequency. Now let's see how the researchers used this amazing coincidence in a surprisingly simple experiment.
The setup itself is incredibly straightforward. You take your superconductor, you carefully lay a super thin sheet of the boron nitride right on top of it, and then you just watch. You measure the properties of the superconductor to see if the mere presence of the boron nitride and all its resident virtual photons is having any effect at all.
So what happens? What happens when these virtual photons get right up next to the superconductor they're perfectly tuned for? Does superconductivity get stronger? Does nothing happen? Well, the actual result was a pretty fascinating surprise.
That's right. The virtual photons actually suppressed the superconductivity. These ghost particles reached out from their material and actively made it harder for the superconductor to do its job. So we've got a clear effect. But how could the scientists be absolutely sure it was the virtual photons causing it?
The proof, as always, is in the details. A classic trait of any superconductor is that it repels magnetic fields, so the researchers checked, and they found that with the boron nitride on top, the material repelled magnets less forcefully. That's a dead giveaway of weaker superconductivity. And of course, they ran controls. They put other materials on top that weren't tuned to the right frequency, nothing. They tried a different but similar superconductor, also not affected. It was only this specific pair, at their perfectly matching frequency, that showed an effect. And you gotta remember, this is all happening in the dark. No real photons anywhere. It had to be the virtual ones.
So scientists use some seriously weird quantum physics to make a superconductor worse. And you might be sitting there thinking, okay, that's a neat trick, but so what? What's the point? Well, the point isn't about improving this one material. It's about what this discovery proves is actually possible.
Yeah, weakening a superconductor is obviously not the goal here. The real value of this research isn't in this specific outcome at all, but in the brand new method it demonstrates. This really represents a fundamental shift in how we can interact with and even understand the properties of materials.
So here's why this is such a big deal. First, it gives us a new probe. We can now study the inner workings of these exotic materials by seeing how they react to different kinds of virtual photons. Second, it's a totally new lever. For decades, the only ways to control superconductivity were cranking up the pressure or dropping the temperature. This experiment proves there's a third way, a quantum way. And finally, this just blows the doors open to new possibilities. It suggests we might be able to change a material's properties not by messing with its chemical formula, but just by changing its quantum environment.
And that leaves us with a pretty fascinating final thought, doesn't it? This experiment used one specific quantum effect to influence one specific material. But what it really does is prove the principle that this invisible virtual world is not separate from our own. It's interacting with it all the time. The question now is, what other ghostly effects are just waiting out there to be found? And how could we maybe harness them to engineer the world in ways we haven't even begun to imagine?